We're starting?
This is fine.
Okay, next, our next speaker is going to be talking about performance and benchmarking of NVM systems. Dr. Ethan Miller from the University of California, Santa Cruz. And so Ethan, why don't you take it away? Oh, actually he asked me to say, so in addition to being a professor out of he felt it's important. He also works 1 day a week at Pure Storage as a consultant. So there's given that, you know, there's an industry audience here, he wanted you to know that as well. It's not pure professor, but also some consulting work. So Ethan, it's yours.
Thank you. So the reason I wanted to make...
Oh, actually, one more thing. So Jim just reminded me. So there are people in the overflow room right now. And so for those of you in the overflow room, that's, you know, it's not ideal. As I said earlier, the room holds about 250. We had 607 pre-register. I don't know how many are showing up. We did put the overflow room in. This is obviously the biggest turnout we've had for this. This is the fourth one. There are some seats up here in the front. Those of you who are standing in the back, if you come up to the front tables, there's some seats left. So coming up the sides or whatever, and find yourself, you actually get the best seats. So come on forward. Okay, Ethan, it's your show.
Thanks. All right, so what I want to talk about today is why it is that the benchmarks we're using now are not going to be good enough for non-volatile storage. And we're already seeing this start to happen with flash. And when we get NVM, which you just heard a good talk about, when we get NVM, we're going to get even worse. And I'll talk about why that is. Okay, so first question you want to ask when you want to know what's wrong with benchmarks is you have to ask, why even bother running benchmarks in the first place? After all, we could just plug this stuff in and use it, right? Well, there are a couple things here. First of all, we want to understand the limitations of a storage system. So we just heard that NVM is up to 1,000 times faster, and the SSDs we made were 7 times faster. Okay, well, clearly there's something in there that makes it go 100 times slower than it, quote, could go, for some definition of could. So our benchmarks are going to feed into storage system development, because I'm going to guess that Intel and everyone else building this stuff is going to say, you know, we'd like to go from 7x faster to 100x faster. Well, 100x faster doing what? That's the question, right? Another thing we want to do with these benchmarks is compare storage systems to one another, because I know everybody here works in industry and you're all working on different competing products, and you know, you'd like to be able to get judged on your merits. Is our system better than your system for a particular thing? And hopefully, if it's better, you get more money, you're more likely to get the sale. That's a good deal. So it's good for comparing things, and it's also good for predicting performance. If I plug in, you know, because obviously if I'm going to spend money on a new SSD, I want to know how much faster is it going to run, and I don't want to go to the trouble of actually buying it and installing it, only to discover, yes, it runs much faster, and you get a 1.5x speed up. Yeah, not so good anymore, right? So I want to use benchmarks for all those things. And the reason for talking about this is when you talk about limitations of benchmarks and what we need to change, it's kind of good to know what we're going to do it for, right? Now, of course, everyone's going to say, wait, but we have lots and lots of benchmarks. I mean, look, we got all these benchmarks over here. Why do we have to change them? I mean, these are pretty good, right? Well, the fact is that there are limitations to this. By the way, for those of you taking pictures, these slides are going to be on the website, so you don't have to worry about that. And if they weren't, I would happily send them to you anyway. So the question then is, what makes a benchmark? So we'll talk about what are the parts to a benchmark, and then we'll talk about what has to change the most as we move to non-volatile memory. So there are 5 things you want to worry about for a benchmark. The first one is location. Where are the requests going to? You want to worry about how big are the requests. Is it a constant size? Is it variable? What's the distribution look like? You want to worry about access type. What kinds of requests are there? Are there block requests or file requests, or perhaps other? And we'll see NVM may end up being a lot more of other than what we have now. And then we run into things like content. What data is actually in the request for writes? And this turns out to be very tricky because for a very long time, it was totally ignored by most benchmarks. There are a large number of older benchmarks that do one of 2 things: write all zeros or all constant, Fs or something else, or write random data. That was the standard way to do benchmarks for a very long time, and we'll talk about why that's a terrible idea for NVM. The last thing is, of course, timing. When do you make the individual requests? And it turns out that timing, and our group has done some work, some research in this area, benchmark timing turns out to, in most cases, suck. Because the general approach to benchmark timing is just issue the request as fast as you can until the system falls over and dies. We'll talk about why that might not be the right way to go for non-volatile memory-based systems. And we'll talk about both flash and NVM because they're both very different from the traditional disk that everybody wrote benchmarks for. Okay? So the first thing you want to worry about is location. Where are the requests being made to? Okay, and it's not just a matter, by the way, of where they're made to, it's also a question of ordering. So let's start off with disk, because yeah, we're talking about things that are really slow, but we're also talking about it in a way that this is the way people wrote benchmarks. Seek times on disk, everyone knows this, they're location dependent. And of course, if you virtualize storage, it muddles this a little bit. So used to be that if you had things that were near each other that would have a short seek time, further away it would be longer. Now you virtualize storage, and a lot of disk systems do it today, and that relationship's a little bit muddied. Well, we've got NVM, and NVM doesn't have seek times, right? I mean, latency is the same to everywhere, isn't it? Well, if you're reading and writing to a raw flash drive, or raw flash, or raw NVM, that's pretty much true. Assuming it's not in cache, the latency is about the same for anywhere on the device. Except for one small problem. You know, remember we said that disks are virtualized pretty heavily? SSDs and NVM are virtualized way more heavily than that. And so the question here isn't where is it physically located, it's rather software overhead, okay? This is why when you talk about a block-based storage device built around Crosspoint, it's 7x faster and not 1000x faster. There's software in the way, okay? And this is where the benchmarks actually really have to be written properly, because access order turns out to be a really big problem and a really big influencer on actual access times, because the software inside your device, whether it's flash-based or NVM-based, is going to build its own internal data structures. So for flash, a common thing to do is to do copy on write or out of place write, where you don't overwrite things directly, you write them somewhere else. What does that mean? Well, it means that if I access things in one order, I write everything sequentially this way. If I overwrite things randomly, all of a sudden I have more garbage, which means things are in different places, I have to look in more places for them. That slows down your system, right? So a disk usually didn't matter. You can write it in any order you want, it would kind of be readable in the same time. Flash, if you write it in one order, like this, okay, you actually can run very quickly. So let me give you an example. Suppose you're running a benchmark, and you say, you know, I'd like to pre-populate my system with data. Known data, so I know I get the answers back, so it's got reasonable stuff. What do most benchmarks do? They say, you know, I'm going to start at the beginning of a range and just write the whole thing like this. Well, you know, here's the thing. That is the best case scenario for most storage systems. Why? Because you wrote the data exactly once, you never touched it, you never overwrote it. Your data structures are clean, they're pristine. You look in one place, you find the data. Now, here's the question. Do real storage systems users actually do this? No, they don't do that. They write it randomly. They load this virtual machine, and while they're doing it, they load another one, and while they're doing this, they're using it for something else over here. Your storage system, which you loaded nice and clean, is the best case scenario. And it's totally unrealistic. But yet for benchmarks, that's what everybody does. So in order to make it more fair, they say, you know, we think that if you write it once, that doesn't warm it up enough. Let's write it sequentially 4 times. Yeah, you know, you didn't do us any favors. You just overwrote the thing like this, then you did it again like this, then you did it again like this, and guess what? You still have a really clean system. So you're going to get numbers that are going to be incorrect. A much more realistic approach if you're writing a benchmark is when you load it up to say, look, here's the area I want to fill, and maybe I'll fill it in little chunks, write this sequentially while accesses are going on. NVM-based systems are much more susceptible to performance differences if you mix workloads than disks were. And this is because, at least for flash, there's an asymmetry between read and write. Even for NVM, you're still going to see that, not because the underlying technology has an asymmetry in performance, it does slightly, but more because the data structures have an asymmetry in performance. right? If you try to read while you're writing things, we already know this from some SSDs. A lot of them have largely gotten the problems fixed, but there still are some where if you do reads if you do reads and writes intermixed, the data is laid out poorly on the SSD. We've actually, I mean, again, remember one of the reasons for saying that I work 1 day a week at Pure Storage is we found this out. When we're deciding which SSDs to use in our storage system, we discovered that some of them, if you mix reads and writes, perform poorly. Don't do, if you're going to use them that way, the benchmark ought to reflect it. Okay, because if it doesn't, you can't predict performance. So the next thing you want to worry about is size. Now, for disks, sequential I/O is a lot faster than random I/O, so of course, the bigger the I/Os, the better your performance, right? So for NVM, you might say, I/O size doesn't matter. After all, who cares? 128K versus 16 I/Os at 8K apiece, that should be the same performance, right? Well, in terms of transfer speed, yes. In terms of seek time, yeah, it's pretty much similar. In terms of the overhead the storage system does to actually figure out where the data is and everything else, no. There are a lot of storage systems out there, NVM-based, that if you give it 128K of I/O, it will go and say, oh, this 128K is right here, and it'll get all the location information once. If you give it 16 I/Os of 8K apiece, it does that 16 times. Which one is going to be faster? Now, this is actually a difference between two basic ways of handling storage on at least flash-based systems, and I'm going to guess NVM as well. We don't have a lot of them, so it's kind of hard to say what they will do. But one way to do this, very commonly used, is to use log structuring, right? Everything in a log and overwrite stuff and so on. For a system like that, you can maybe read the whole 128K if you knew where to start. Now imagine that you're talking about a content addressable system, one where you hash the data and look it up by hash. Those 8K blocks are going to be in 16 different places, whether you give it one request or 16. Sequential will be faster here, won't be much faster here. So you really want to make sure you get the right mixture of sequential and non-sequential for NVM because, again, software overheads determine more of the performance than the hardware latencies. Okay? One other brief thing, by the way, to note is that, and we'll talk more about compression later, compression can take your 128K request and make it actually a request to read 50K. But we'll get to compression and data reduction in a bit when we talk about content. So the next thing we want to talk about is access type. Do you have blocks or do you have objects? Well, if you're disk-based, you either have blocks or files. There aren't a lot of object-based systems now, although increasingly you're getting key value stores, which kind of look like objects. Not much properties, but the idea here is that for blocks, there's almost no lookup time on any system to get a block, right? If you have a well-designed disk system, the overhead for a block I/O is almost zero compared to the time it takes to read the block. Talking about files, there's lots of extra overhead for every single operation. Well, systems based on NVM are likely to be different. I mean, initially they're going to be blocks because that's what all the interfaces are. I would be very, very shocked if in 10 years the systems are not based on bytes or objects or key value. Why? Variable size stuff without all the overhead of files, and it turns out that's going to be a very convenient way of doing things. Well, if there are byte level operations, if you're talking about using this kind of like a memory device, you're going to have hundreds of millions of requests per second. We'll talk about that when we get to timing as to why that would be hard for benchmarking. Even if you talk about object-based operations, you can buy flash systems today from a lot of companies that are over 1 million IOPS, and they're not that expensive. There aren't an awful lot of disk systems that support 1 million IOPS. In fact, I'm not sure if there are any of them. Anyone know offhand if there's anything short of Google file system that does 1 million IOPS? Certainly you wouldn't put it in one rack. I mean, you can buy 1 million IOPS in about that much space today from a number of companies, right? So this is going to be an issue. Now we get to the things that matter the most for NVM benchmarks. Content and timing. We'll cover content first. For disk, content doesn't matter all that much because disk systems don't use data reduction for all that, at least the ones that we care about performance for, don't use data reduction aggressively. They tend not to use compression and deduplication. Why not? Real simple. When you buy a disk system, do you care at this point about capacity if you care about performance? The answer is no. If you want a disk system to run at 20,000 IOPS, you're going to need so many disks for it that there's got plenty of capacity for whatever you want to stuff on there. So why, if you were a vendor, would you bother doing compression and deduplication to make it so the same number of IOPS applied to even more storage when you weren't using all the storage in the first place? This is a great idea. Put in more overhead to make sure that you can sell a system at fewer dollars per byte when people aren't paying dollars per byte, they're paying dollars per IOP. Silly idea. So disk systems tend not to compress and deduplicate. What does this mean for benchmarks? It means you can write whatever the heck you want and the disk system doesn't care. You can write all zeros, as by the way a lot of benchmarks did, and the disk system will still just write out all zeros. It's happy to do it. It doesn't know the difference. Well, remember that NVM is different because NVM is expensive. Okay? Yes, I know. We just heard that cross-pipe memory would be cheap, but believe me, not as cheap as disk. I mean, I'd like it if it were, but I'm thinking it's not going to be. Even flash right now is not as cheap as cheap disk. Yes, it is now as cheap as expensive enterprise, the 10K, 15K drives, but that's because no one's buying them to actually get performance, they're buying flash instead. You can still go down to Fry's and buy a 4 terabyte drive or a 6 terabyte drive for about 150 bucks. I don't think that flash, let alone Crosspoint, is quite there yet. So when you have expensive memory for NVM, data reduction helps. If I can compress and deduplicate the data and get 2x performance gain, I'm going to do it. And all of the systems out there that I'm aware of have either got data reduction or going to have it real soon. Now, because they're very fast, a lot of the performance implications go away, which means that all these systems are going to use data reduction and they're going to have some impact on performance, but hopefully not too much. This is where the benchmarks start to become important because how much data reduction you get is content dependent, right? How effective your system is with data reduction is content dependent. So let's see what we mean. First thing is compression. You've got to make sure your data is compressible, but not too compressible. So if you write all zeros, that's compressible data. That's extraordinarily compressible data. In fact, a lot of systems, I know Pure will do this, and I'm pretty sure many others will just issue a trim request. So when you store all zeros, it goes, oh, that's easy, just make it go away. In fact, reading back all zeros is insanely fast. Does that mean that your benchmark should do this? Hell no, because you're not reading back all zeros. That would be silly, right? So people say, oh, great, well, we don't want to do that. We don't want all zeros. We'll just issue random data. Yeah, that's got a different problem. Most NVM storage systems today are optimized for data that compresses. In fact, if you go to most of the major vendors and say, look, I want to store pictures, they're going to tell you that basically, pictures? Why would I want pictures? I mean, after all, if I'm going to store pictures, I'm going to get no compression out of it. So they're going to have data that compresses at about 2 to 1 or 4 to 1, somewhere in that range. Different algorithms compress in different ways, which means that how you generate the data in your benchmark may determine how well system A performs versus system B. You want to make sure your data is generated realistically, because the last thing you want is somebody who uses LZ4 compared to somebody who uses a different compression algorithm. You don't want to say, well, your data was easy to compress with LZ4, hard with yours, when the reality is that real world data about equally compressible. Okay? Now, there are a couple of ways to do this. One way is to simply reuse sampled data. Take data from real world, virtual machines, databases, whatever, swap characters around to protect the names of the innocent, and also to make sure it doesn't deduplicate. More on that in a minute. And if you do this, you'll get realistic data. Now, you could also do something where you generate data that matches that from the systems you've actually deployed. This is harder, but it means that your benchmark can actually generate 5 terabytes of data or 100 terabytes of data without having to have a real system that has that much data to begin with. Well, it turns out compression, not so bad. Deduplication, much worse, okay? NVM-based systems almost always deduplicate, either because they explicitly look for duplicates or because they're content addressable systems, which just deduplicate by their very nature. So benchmarks have to mirror 2 kinds of patterns. One is, how much deduplication is there? What fraction of blocks are deduplicated by how many times? There's a second issue. What order do you see the deduplications in? And this is absolutely critical to make sure you get the deduplication right. Because let's say that I have a block that's going to be deduplicated 10 times. If I imitate this by writing it out 10 times in a row, an idiot will tell me, oh yeah, that's 10 copies of the same block, store it once. What if I write it out 10 times but separate each of them by a gigabyte, or by 2 gigabytes, or 5 gigabytes? Some mechanisms for catching duplicates will work well with that, some won't. right? You want to make sure it's realistic because you don't want to let somebody get away with a free pass just because you happen to issue the duplicate requests too close together. So again, try to figure out for a benchmark where the duplicates lie. So let me give you an example. Deduplication of virtual machines. If I take a bunch of virtual machines and write them sequentially like this, there are systems which will find less duplication than if I write the virtual machines in parallel. Because if I write them in parallel, the distance between this duplicate and this duplicate at similar position in two VMs, it's very small. I mean, you're writing them both in parallel, they both occur pretty close in time, versus, gee, I wrote these 50 gigabyte VMs and now there's 50 gigs before each duplicate. Which one of those is more realistic? I'm not going to try to answer the question, by the way, because that's going to be workload dependent. We'll get to that. Another point here, by the way, is that real-world systems don't write VMs that way. They use Xcopy, right? They use copy offload. Well, guess what? If you use copy offload, you're going to get more efficient. Okay? So the last thing that the next last thing we're going to talk about is time, and timing is really important because existing benchmarks do typically multiple threads and issue the request as fast as you possibly can, which for disk might make sense, okay? Doesn't make sense for NVM. Second problem, of course, is that faster systems need to issue IOs faster. And well, the number of IOs you're talking about is huge, okay? We'll get to that in a minute, right? Instead of issuing requests as this one issued, then it finished, then this one issued, and so on, a better approach, and one that we've looked at, is to issue IO requests at a fixed rate and see whether your storage system can handle it. Because in most cases, you're not going to run, for modern applications, at 2 million IOPS. What you want to know is, if I issue requests at 50,000 IOPS in this pattern, will you be able to handle the request? Okay? So instead of issuing them at, just back to back as fast as you can, you want to issue them at a fixed rate. And when I say fixed rate, I don't mean necessarily every 10 microseconds. There's a distribution. It's a Poisson arrival, it's uniform distribution, whatever distribution you want, and the rate itself might vary over time. You might have a benchmark that goes higher and then lower. Now, that way, if you're a faster system, you're not penalized by somebody saying, oh, you're faster, here, do more stuff. Something that happens at a university all the time. Oh, you actually get things done, here, have more things to do. Trust me, you don't want that, okay? This is really important when you have an NVM system that runs at 1 million IOPS. You want to make sure that it's not penalized for being able to run so fast. You want to make sure it gets the same workload as somebody whose maximum speed is 300,000 IOPS. Benchmarks aren't very good at that. They're also not very good at issuing requests at 1 million IOPS in the first place. Okay? When you're benchmarking a disk system, you've got to issue them at 50,000, 100,000 IOPS. Yeah, no problem there. But what about systems that run at 2 million IOPS? Benchmarks aren't designed for that. They're really bad at it, and they're even worse at it because we're going to need to use multiple threads. Multiple threads sounds like no problem, right? But it turns out that multiple threads is very hard if you want repeatable benchmarks. Everyone says, oh, use pseudo-random number generators, that'll make it repeatable. Yeah, only if you happen to have the same threads using the same numbers in the same order, which is not the way most benchmarks use. Now, deterministic random number generators, we got those, they're easy, no problem. But what happens when you have 20 threads issuing IOs, right? How do you get the numbers to be repeatable? So we need to use the random numbers in a fixed order, and one of the ways we're looking at doing that is to have a centralized random number generator and a centralized thread that generates the workload, and then all the other worker threads pull workload off the buffer. That's not the way that benchmarks are written today. But if you want repeatable stuff, that's what you've got to do. Okay, so the last thing I'm going to talk about is the elephant in the room, and that is, so what is workload going to actually look like? Okay? What workload is actually going to look like, right, is, well, we don't know. We know what it looks like today, but if you tell somebody they can have 1 million IOPS at microsecond latency, how are they going to use the IO? Anyone here know the answer? By the way, if you know the answer, do a startup and make a bunch of money. Because we don't know the answer to this, right? We don't know what the access pattern will look like because we don't have these devices yet. Right? So you're trying to guess at what the access pattern is going to look like. You can say, well, it looks like what it does now, except that that's already different. Key value stores, for example, new thing, run great on SSDs. If we had to stick with disk versus flash for key value stores, they'd run much slower. They wouldn't see the adoption rate they do today, right? So we really want to know what is the access pattern going to look like, and we don't know the answer. Now, this is going to tell you what you need to look for to build new benchmarks. I'm not going to stand here and tell you exactly what to put in there because I don't know the answer either. And if you, as I said, if you do know, please tell me because I'd like to know myself. So to sum up, the implications for benchmarks of having non-volatile memory are a couple of them. First one is the benchmarks have to be accurate. The faster the system runs, the more you care about the benchmark actually modeling what happens in reality, and the more that the benchmark is measuring software performance, as it is for NVM, versus hardware performance, the more that you care about it being an accurate model of what really happens. Second thing, of course, is that benchmarks need to be faster. 2 million, 5 million IOPS, yeah, that's not that unusual, right? Benchmarks don't do that right now. You can't even build that in hardware. The benchmarks also need to be deterministic because the last thing you want is to run the same benchmark twice and discover you have, well, the equivalent of a Heisenberg. I ran it once and that problem showed up. I ran it again and I don't know what happened. So achieving all of these goals is going to be really difficult, and it's a challenge for the community in how to do this. And with that, I don't know if we have time for questions. My watch says 9:58, so we got about 2 minutes. Okay, so I've got about 2 minutes for questions.
Ethan?
Yes.
Here's a question from the overflow room.
Okay.
The question is, when will benchmarks start measuring I/O impact on overall machine performance? And his specific question is instructions wasted per I/O.
So instructions wasted per I/O, I guess can't do back and forth. The question here is, how do you determine whether it's, measure the impact on perhaps operating systems? The answer is it already does to some extent, right? Because if you issue the request through the system stack on the machine, you're going to measure that. Now, that's going to measure it on whatever machine you run the benchmark on, not on whatever machine your actually final application runs on. Unfortunately, the only way to do that is to actually measure the real application performance because different applications will have different overheads. I mean, there's unfortunately no good way to do that. Yeah?
I'm wondering about scaling up of lower level architectural hardware features like TLBs.
So TLBs, so are you talking about doing this in the client machine or in the storage system?
I'm talking about how it changes the balance of that software overhead that we talked about.
Right, so you're talking about in the storage system.
Yeah,
So
in the memory subsystem.
well, but here's the thing. If you're using, so this is the question then is, are you going to use NVM-based storage, NVM-based storage as a memory device or as a storage device? Okay, and that's a very bottom level question. My point of view, by the way, is you're going to end up wanting a storage-like interface simply because at some level you have to treat this like a little bit differently than you treat direct attached storage if you want to be able to share it very efficiently between systems. If you are going to use it as directly attached memory, then yes, TLB performance matters, and that's going to be a question for the virtual memory subsystem. So there you might even have to have a benchmark that instead of doing explicit I/O requests, just does random reads of something that's mapped into your memory. That's going to make the benchmarks look even more different, and I wasn't going to go that far. We have memory benchmarks, but I don't know if that's the right way to go with that. Yeah?
Last question.
Yes, so all the recent NUMA systems are inherently random because of the temperature of scaling issues. So how do you propose to
When you say inherently random, what do you mean? Sorry, your question was that all of the NUMA systems are inherently random because of temperature and clock scaling. But when you say random, what do you mean?
Well, you can't control the temperature of the enclosure of the room and so on.
That's right. But again, if you have a single thread generating requests and then you have worker threads pulling the requests off, that solves the problem because the determinism comes in, issue the request in this order at this time, right? Whether I have 20 threads or 100 threads or 500 threads, I pull each request off at the time it's supposed to happen. There's determinism in the thread that generates everything. And then these worker threads issue them in the right order. Now, the results may not be deterministic, but at least the workload is. I mean, I can't guarantee deterministic results because I don't know about the storage system. That may not be deterministic itself. Okay.
Thank you, Ethan.
Great.
Okay, our next speaker is Ken Gibson from Intel. As a